As with single populations, now we have found fixed points for a population system, we again want to find the stability of these points. Also, as before, we define n hat t and p hat t to be small changes from the fixed point, such that the population of n at t is equal to n star plus n hat t, and population of p at t is p star plus p hat t. Now, substituting these into our governing equations gives us n star plus n hat t plus 1 is equal to f of n star plus n hat t, p star p hat t, or plus p hat t even, and p star plus p hat t1 is equal to g of n star plus n hat t, p star plus p hat t. Taking a Taylor expansion of the right hand side of this gives us n star plus n hat t plus 1 is equal to f of n star p star plus the partial of f with respect to nt times by n hat t plus partial of f with respect to pt times p hat t plus some higher other terms. In the other part of this equation is p star plus p hat t plus 1 is equal to g of n star p star plus the partial of g with respect to nt times n hat t plus the partial of g with respect to pt times p hat t plus some higher other terms, where the partials are evaluated at the point n star p star. Now, from the definition of a fixed point, we can see that f n star p star evaluates to n star and g n star p star will evaluate to p star, allowing them to cancel with the terms on the left. This will give us n hat t plus 1 is equal to the partial of f with respect to nt times n hat t plus the partial of f with respect to pt times p hat t plus some higher other terms. And similarly with p hat t plus 1 is equal to the partial of g with respect to nt times n hat t plus the partial of g with respect to pt times p hat plus some higher other terms. Since this is a linear stability analysis, we are not interested in nonlinear terms, so that by removing these higher other terms, we get to, assuming that n hat and p hat are small, we can write the entire model as a linear system, which is given by the column vector of n hat t plus 1 and p hat t plus 1 is equal to the matrix partial of f with respect to nt, partial of f with respect to pt, partial of p with g even with respect to nt, and the partial of g with respect to pt, times by the column vector of n hat t, p hat t. We can see here that a is just the Jacobian of our governing equations, and we can now define this system as w of t plus 1 is equal to a times wt, where wt is the first column vector and is the second one even, and wt plus 1 is the first column vector of n hat t plus 1 and p hat t plus 1. Given that the solution takes the form wt is equal to sigma from I to 2 of ci times lambda I to the power t times ei, where ci's are constants determined by the initial conditions, and lambda I and ei are the eigenvalues and eigenvectors of the Jacobian, we can see from this that the fixed point is only stable if the modulus of the eigenvalues are less than 1 for all eigenvalues, as raising these to the power of t will either tend to infinity or 0 depending on the size of the eigenvalue. To see how we can apply this, we will now look at an example. In the last example, we looked at the Nicholson-Bailey model, which, to remind us, is nt plus 1 is equal to r0 times nt times e to the minus apt, and the term for population p is pt plus 1 is equal to c times nt times 1 minus e to the minus apt. The Jacobian of this model is given as r0 e to the minus apt minus a times r0 times nt times e to the minus apt, c 1 minus e to the minus apt, and ac times nt times e to the minus apt. Now, looking at this Jacobian for the fixed point of 0, 0, which is our first fixed point of the system, we get that a is equal to r0, 0, 0, 0. The eigenvalues of this, by fairly simple inspection, is lambda 1 is given as r0 and lambda 2 is given as 0. So, considering our definition for stability, if r0 is greater than 1, the fixed point is unstable, and if r0 is less than 1, then the fixed point is stable. Or modulus of r0 is less than 1 even. Now, considering that the other fixed point of this system, found in the previous video, which we found to be r0 times the natural logarithm of r0 divided by ac times r0 minus 1, and 1 over a times the natural logarithm of r0. In this case, the Jacobian evaluates to a is equal to 1 minus a times r0 times natural log of r0, all divided by ac r0 minus 1, c times 1 minus 1 over r0, and ln r0 over r0 minus 1. Sometimes, as in this case, it is not practical to find the eigenvalues of the system. In this case, we can use the jury conditions to analyse the stability of these fixed points. The conditions are given as b is less than 1, b plus a plus 1 is greater than 0, b minus a plus 1 is greater than 0, where a is the negative trace of the Jacobian and b is the determinant of the Jacobian. To see where these conditions come from, refer to the video about the jury conditions themselves. So, from our example, we can see that a, which is a minus trace, is minus 1 plus natural log of r0 divided by r0 minus 1, and b is equal to the determinant, which is equal to r0 times the natural log of r0 divided by r0 minus 1. So, to look for the first condition, we see that r0 times the natural log of r0 divided by r0 minus 1 has to be less than 1. This implies that the natural log of r0 has to be less than 1 minus r0. So to check this condition, we define the two functions f1 and f2, where f1 is the natural logarithm over r0 and f2 is 1 minus 1 over r0. So noting that at r0 equals 1, f1 equals f2, and they both equal 0, we can then look at the derivatives of these functions with respect to r0. So the derivative of function 1 with respect to r0 is 1 over r0, and the derivative for function 2 with respect to r0 is 1 over r0 squared. So when r0 is greater than 1, the derivative of f1 is greater than the derivative of f2, which tells us that f1 is greater than f2 when r0 is greater than 1, which is a contradiction to our condition, and so the fixed point is linearly unstable. This is how you evaluate the fixed points and their stability in a multi-population system in discrete time.